When an object moves in a circular path, it requires a certain set of forces, centripetal forces, to keep it moving in a circular motion. In order to understand the calculations and the variables behind circular motion, we need to do a little vocabulary first. When we talk about radius, we are talking about the distance from the center of a circle to the loop. The period is the time it takes for the object to make one revolution. So the period is in seconds, it's a measure of time. One revolution is one lap, so one full trip around the loop. The frequency is the number of revolutions made each second, so it's the reciprocal of our period. Period is seconds per revolution, frequency is revolutions per second. The velocity is the straight line speed that it would go if the object flew off the loop. So if the string were cut, it's how fast that object would go in a straight motion tangent to the circle. The mass is obviously the object going around the circle, and the centripetal force is the force exerted toward the center of the circle, which makes the object go in a circle. When we talk about these equations, the variables and the units are very important. They help us find our given information and help us communicate our final answers. The radius is represented by r. It's measured in meters. T, or capital T, is the period. This is measured in seconds. Remember, this is how many seconds it takes for the object to make one revolution, one trip around the path or loop. F, or lowercase f, is frequency. This is revolutions per second. It's the reciprocal, or the inverse, of period. This is also called hertz. Revolutions per second is also called hertz. The velocity is going to be in meters per second, as usual. Mass, as always, is kilograms. Centripetal force. This is another variant of forces. Just like F sub g was gravitational force, F sub n was normal force. F sub c represents the centripetal force. This can be any force that keeps an object moving in a circular motion. The unit for this force is newtons. We'll talk about the different forces that make up centripetal forces in a moment. Because the force exists and can exert on a mass, there's an acceleration, a centripetal acceleration. So you put that A sub c to represent this specific type of centripetal acceleration. A centripetal force is not a new force. It's anything that can exert a force can exert a centripetal force. So a rope or string, which would be a tension force, this can represent centripetal force. It can keep an object moving in a circle. Gravity, so like the planets rotating around the sun. The gravitational pull between the Earth and the sun keeps us in orbit around the sun. Friction. When you drive a car around a curve, the friction pushes you inward. It keeps you moving in a circular motion. A wall or a surface of any kind can provide a normal force. Great example is the gravitron. All of these forces, tension, gravitational, friction, or normal force, can all represent centripetal force as long as they're keeping an object moving in a circular path. Just like drag or lift forces represented other things, just like air resistance represented friction. Let's look at an object overhead as it's moving in a circle. So in this case, let's pretend it's an object on a string. So it's a tension force swinging an object in a circle. If while we're going around, that string broke, that object would keep moving in a straight line. It would not move with the curve. Inertia would say an object in motion tends to stay in motion. So that object is going to keep going completely straight. We would call that tangent to the curve. That means it's a line that only has one point that crosses over with the circular path of the object. The direction an object flies off the off the circle has a specific name. So again, this is tangent to the curve. So no matter where it's cut, where that string's cut, it's going to be tangent. It's going to make a right angle with the radius, which in this case is the string that's connected from the center of the circle out to the object. In this case, with a string, we're creating a tension force, but it's a centripetal force. What is the direction the force is acting on the object that causes it to go in a circle? Well, if I was swinging something over my head on a string, I'd be pulling inward. So the force is pulled towards the center. If we look at the word centripetal, centra means center. This is a center-seeking force. When I spin the string around my head like a lasso, I'm pulling the string in constantly, and that creates a centripetal force, allowing the object to move in a complete circle. When you move in a circular path like this, whether you're on a carnival ride or going around a curve in a car, you feel like you're getting pushed outward. There is no force that's pushing you outward. What's happening in those cases is your inertia wants you to keep moving. So even though the object or car that you're in keeps moving, your mass, your personal velocity wants you to keep moving, so you run into the side of the object that is in a circular path. So even though the object is being pulled towards the center, so in this case the car, you feel like you're getting pushed forward or pushed out against the side of the car. This is just your inertia, your momentum pushing you forward. Whenever we have to calculate centripetal forces, we're going to use some of the same force equations we've used before. So we're looking at Newton's second law. This is the net force equals mass times acceleration. Using this, we were able to calculate the velocity, which gave us the acceleration. We're able to measure the mass of the car, and then by doing that, we can find the centripetal force. Using these formulas, we can find the velocity, the period, the frequency, etc. So there's three variations of this force, or this formula. When velocity is involved, we're going to use mass times velocity squared divided by radius. When the period, so the time it takes to make one revolution, is involved, we're going to use mass times pi, which we can just round to 3.14, or use the pi key on your calculator. So mass times pi squared times radius divided by period squared. So remember, that's t, that's the time it takes to go around one revolution. If the frequency is involved in the scenario, we're going to use mass times 4 times pi squared times radius times frequency squared. Remember, the frequency is the amount of revolutions in 1 second. Period and frequency are inverses. They're reciprocals of one another. A period of 1/3 would be a frequency of 3/1, and vice versa. Notice in each scenario, if I'm finding the force, I have to find the mass. The formula we've dealt with before, force equals mass times acceleration. If I cut out the mass from each of these formulas, I'm left with just the acceleration of each version. So if I'm dealing with the velocity, I have a formula for finding the acceleration, v squared divided by r. If I'm dealing with the period, I'd find a formula 4 times pi squared r divided by t squared, which is the period squared. That's my acceleration there. If I'm dealing with the frequency, I'm going to find acceleration by doing 4 times pi squared times r times frequency squared. These are all just the portion of the formula for the centripetal force that doesn't involve the mass. So if I know the acceleration, I can multiply by mass to get the force. That's a shortcut moving forward. Just like the kinematic equations, each formula has a specific use. If you're finding the force, you always need the mass, you always need the radius. So you'll always need the mass and the radius, but depending on what you are given besides those two, so if you're given velocity, period, or frequency, you can either choose the right formula for force or acceleration.